Okay, guys, so this is the second last lesson out of this momentum and energy section. Now we're going to start looking at two-dimensional momentum. So we said before that momentum was a vector because velocity is a vector and momentum is mass times a velocity. When you multiply a scalar by a vector, you get a vector. So how we deal with these things now in multiple dimensions is going to be similar to how we dealt with kinematics in multiple dimensions. We have to add vectors together appropriately. So here's our first example. If we have a 2 kilogram object moving at 5 meters per second at 20 degrees west of north, so we got 20 degrees west of north, and this thing has a velocity here of 5 meters per second. We want to find the momentum vector, and we want to find its components of momentum. So if we look at this, the momentum vector here, part A, we want this thing in polar coordinates. If you remember what polar coordinates are, it's the momentum, the magnitude of the momentum times with the direction in degrees. And then in components, we're looking at I hats and j hats, or x and y components. Components. Okay, so here we go. The momentum vector is easy to find. Momentum p, our vector, is equal to our mass times our velocity. So our mass of our object, we're told, is 2 kilos. So it's going to be 2 kilograms times the 5 meters per second, which is going to give us a momentum vector of 10 kilogram meters per second, and the direction is the same. We're just multiplying this thing by a scalar, so it's making it longer. So this is going to be 20 degrees west of north. So now we want to go through, we want to find these components. So if you remember what the components are going to look like, the components are x, or that's y, and this is x. So I'm going to call this momentum in the y direction. I'll call this momentum in the x direction, and we want to figure out what those things are to put this thing together properly. So the momentum in the x direction is it's moving to the left, so it's negative. And you can see here, if you remember, components always meet at 90 degrees, so this is a 90-degree triangle, so we can use, in this case, px is the opposite from our angle, so we're going to use sine. That's going to be the hypotenuse times the sine. The hypotenuse in this case is 10. That is the momentum. Put that in here. P equals 10. I don't need that. P equals 10. So it's going to be 10 sine 20, which is going to give us an x component of negative 3.42 kilogram meters per second. And then our our y component is going to be, it's up, so it's positive, and it's going to be 10 cos 20, which is going to give us a value of 9.4 kilogram meters per second. So in component notation, we've got negative 3.42 I hat plus 9.4 j hat. And we just put the units there at the end. So we've got to make sure that we're dealing with momentum proper, not just velocity. We have to multiply the velocity by the mass to give us the momentum. And then we're breaking these things up into components, just like we were doing before. Up and right are inherently positive, left and down we treat as negative. And so here we go. So let's actually look at an application of this. Problem's going to look a little gross, but that's okay. Here we go. We have a 3.5 kilogram mass moving with an initial velocity of 5.1 meters per second southeast. And so we know southeast, we know some things about southeast, so it's going that way and it's going that way. Southeast means that this angle in there is 45 degrees. It hits a barrier and reflects so that its final velocity is 4.2 meters per second, 60 degrees west of south. So that means is that this guy here, did I draw that wrong? I did draw that wrong. That's okay, we can fix it. West of south means that's 60 degrees there. For the sake of the lines I've already drawn, that's going to make this guy 30 degrees. There. 60. I'll zoom in a little bit here so you can see them better. So let's go through and, well, let's finish labeling some stuff here. We know the mass of this thing, it's the same object, so I only record that once, is 3.5. We know that the velocity here is VI equals 5.10, and the final velocity here, VF, equals 4.20. So we want to look at this thing. If the collision with the barrier took 0.52 seconds, we want to find the force that acted on the mass. Okay, here we go. So we can see here we're dealing with force and time. So if we flip back and look at our, maybe I have an easier one to grab. No, if we flip back and look at our formula sheet, if we're dealing with momentum and we're dealing with force and time, what we're addressing here is this guy right here. We're addressing impulse. F delta t equals m v final minus v initial. So this is the equation that we're dealing with here. F delta t equals m, and we want our velocity final minus our velocity initial. Now we could do this whole problem with sine law, cosine law, if we wanted to. The math there gets a little bit convoluted. I can show you that if you want. Fire me an email if you'd rather see it done that way. But for the sake of simplicity here, I'm going to break this thing up into components. So we're going to break into components. What that's going to give us is it's going to give us this. We're going to have an fx delta t equals m v final x minus v initial x. And it's going to give us, we're going to drop down here a little bit, create some space. It's going to give us fy delta t equals m v final y minus v initial y. And then we can put it back together and get the whole force. So let's break these guys up into components. This here is Vx initial, Vx initial. This is going to be Vy initial. This is going to be Vx final, and this is going to be Vy final. Now, again, we've already seen that components can meet at 90 degrees. So these will be relatively easy to do pretty quickly. And again, this time I'm dealing with the velocities, not the momentums. So we're going to leave this as the velocity here. So Vxi is, this is going to be 5.1 cos 45, and it's positive because it's moving to the right. So this is going to be 3.61. And this guy is negative because he's moving down, and this is going to be, well, it's going to be 5.1 sine 45. I'm running out of space here, so I'm just going to put the answer. That's going to be negative 3.61 because it's going downwards. This guy over here, again, just the way I drew it, I'm going to use this 30-degree angle in here, even so because they gave us 60 degrees west of south. The way I drew it, we're going to use that 30. So Vx final is going to be, he's going to the left, so it's going to be negative 4.2 cos 30, and so that's going to be negative 3.63. And then this guy here is going to be negative 4.2 sine 30. So that's going to give me a Vy final of negative 2.1 because he's going down, so he's got to be negative as well. So I'll move that over. So now let's do this. We've got, we're looking for our components of force. So we've got Fx, we know the time it took, 520 seconds, equals our mass, which we've got, 3.5. Our V final x is negative 3.63. Minus our V initial x is 3.61. If you solve this thing now, this guy minus this guy times this divided by that, you're going to get an Fx of a negative 48.75 newtons. Slide this guy down here a little bit so we can do the same thing down here. We're going to get Fy, the time doesn't change, 0.52 seconds is going to equal the mass doesn't change. Now we're just dealing with a final y, which is negative 2.1 minus, now our initial y is negative 3.61. Don't mess up these negatives here. Make sure you're really deliberate about how you're going through it. It's minus, and then go get the number. The number happens to be negative, so we're going to have that double negative in there. So if we solve this thing properly, this minus negative this, or this plus, negative 2.1 plus 3.61 times 3.5 divided by 0.52 is going to give us our y component there, where if you plug that through, you should get 10.16 newtons. So here's what we've got. We've got a force acting on our object, if we bring these guys all back in together, of negative 48.75 I hat plus 10.16 J hat newtons. And so if you look at what this means, I'm going to redraw this picture just kind of right here. We've got a ball coming in that way. It rebounds off going that way. So in order to make that happen, we have to have a force that looks something like this. It's going to have to be to the left, and it's going to have to be slightly up. Because this guy's coming in downwards here, so this, if we remember, this angle here was 45 degrees, but this angle here now is 30 degrees. So we've shallowed the angle, so we're going to have some of that upward, some upward force here. So this, if we look at it this way, our results do kind of make sense. So now I just want to find, so I've got my force there, I want to find this thing in terms of its magnitude and direction. So this is 48.75 acting to the left. This is 10.16. So this, my magnitude of my force is that guy there. So that's going to be the square root of 48.75 squared plus 10.16 squared. This is going to give us a total force of 49.8 newtons. And we want the direction. The direction is going to be the tan inverse, so this is the angle we want in here. The tan inverse of opposite over adjacent, so that's going to be the tan inverse of 10.16 over 48.75. It's going to give us a direction of 11.77 degrees north of west. And we're just going to put that right here, 77 degrees north of west. And that is the force acting on our object. And so in this case, we broke up the velocities into components instead of the momentums, because we made it a momentum and we multiplied there by that mass. So there you go. Zoom that out and take a look at the whole problem. Pause it if you like. And we're going to move on to the next one. There's a number of examples here I want to go through with you guys. This lesson's pretty long. Here we go, example 3. Now we're going to start looking at collisions. What happens if we take two objects and we smack them into each other? What does a two-dimensional collision look like? So once again, for a closed system, momentum is conserved. Nothing's acting in on the outside. We have two objects, they're going to smack into each other, momentum is conserved. This means that the momentum is conserved in both component directions, horizontally and vertically, so we're going to end up splitting this problem like this. We're going to have a horizontal momentum, and we're going to have a vertical momentum, and then we're going to put it all back together at the end. So we want to, ultimately what we want to find here is the velocity of the 10 kilogram mass after the 2 kilogram mass moving at 8 meters per second east hits the 10 kilogram stationary mass. Knowing that the 2 kilogram mass moves off, I'm going to add a line in here. So that angle in there is 10 degrees, 6.7 meters per second south of east, so that's that angle there. And we want to know what this guy's doing up here. So ultimately what we've got here, it's a collision, so we're going to deal with momentum. Momentum's going to be conserved. So my momentum initial has to equal my momentum final, but now we're in two dimensions, so these are vectors. What that means is my momentum initial in the x direction has to equal my momentum final in the x direction, and my momentum initial in the y direction has to equal momentum final in the y direction. And this is where the problem splits. Initial, final. So let's write down what we've got. Initially, the mass of 2 kilograms has an initial x velocity of 8 meters per second. We're told it's moving due east. Because it's moving due east, the initial y momentum is 0. And then this guy here, the 10 kilogram mass, is stationary, so his initial x and his initial y are both 0. Now we've got two, they don't stick together, they split, so we're going to have to deal with them separately. We're going to have a mass of 10, a final y of, we don't know, and a final x. Actually, I'll leave it the way, the same order I had before. X then y. We don't know. We're looking for those two values. And this guy down here is going to have a mass of 2 kilograms, a final x, and a final y. These we can find. We told he's moving at 6.7 meters per second. So it's going to be 6.7, 10 degrees south of east. So the x component is east, so it's going to be positive, so it's going to be 6.7 cos 10. The y component is downward, so it's going to be negative 6.7 sine 10. So we can find that this is 6.598, and this guy down here is going to be negative 1.163. Both of those are meters per second. And so now we can go through, we can set up our momentum questions, and we can figure out what these two components have to be, and then rebuild it to find the magnitude of the velocity. Simple. So here we go. We're going to have m1 v1x plus m2 v2 1x initial x2 initial equals m1 v1 x final plus m2 v2 x final. So this is going to be 2 times 8 plus 0. We like that. That's going to equal the mass of 2 times 6.598 plus the mass of 10 times v final x, that guy we're looking for right there. We can go through, we can solve this relatively easily. We're going to get v final x is going to be 0.28 meters per second. So that's this guy there, 0.28 meters per second. And we're going to do the same thing now for our y components. So I'm going to get m1 v1 y initial plus m2 v2 y initial equals m1 v1 y final plus m2 v2 y final. There we go. This one's actually really nice because if you look at this, neither of them have initial y components. So this guy's going to be 0 and this guy's going to be 0. We like that a lot. This guy down here is going to be 2 times, and he had an initial or final y component of negative 1.163 plus 10 times v2y final. So we multiply these together. We're going to add it over because it's negative here. We're going to divide by 10, and we're going to get a v2y final of 0.23 meters per second. So then up here, 0.23 meters per second. Those are my x and y components. So if we draw those in, we can see that there's my x, there's my y. My x was 0.28, my y was 0.23. That's really hard to see. We want to get the magnitude of the velocity here, so we're going to get v equals the square root 0.28 squared plus 0.23 squared. And so we're going to get a velocity of 0.364 meters per second. Our velocity. And then we want this angle in there. That's going to be the tan inverse. I'll put that over here. Tan inverse of opposite, which is 0.23 over adjacent, which is 0.28, is an angle of 39.5 degrees. So we're going to get a velocity of 0.364 meters per second, 39.5 degrees north of east. Which is kind of what we expect. If we have a 2 kilogram object, an object that's 1/5 the mass, coming in hitting a stationary 10 kilogram mass, this guy's going to bounce off a lot harder. He's going to be moving a lot quicker. This guy is going to be moving a lot slower. Ultimately, mass, or momentum rather, is still conserved. And it does kind of align with what we expect. So there is the entirety of the question. There's some. See if I can focus it up a little bit better for you guys. There you go. So we are going to do 2 more examples. I'm not going to do all of the examples that are present, but we are going to do 2 more. We're going to use energy now. So we're going to take this exact same example, and we're going to look at what happens with a collision, with that same collision, in regards to energy. So we want to find the kinetic energy lost. So the fundamental difference here, momentum is conserved. Energy doesn't have to be. In fact, we know it's not. Actually, we don't know it's not. It could be. If it sticks together, we know energy is lost, but they're bouncing off, so energy might not be lost. If there's no energy lost, this is a completely elastic collision. But if there is any energy lost, it's an inelastic collision, so that's what we want to figure out. Remember, energy is not a vector. So there's no components that we have to consider. We just want to know, we're going to use the work energy theorem. We just want to know the energy each object has before and after the collision and then any work done. So we're assuming that these things we're looking at these things from the top down, so there is no potential energy changing here. Yes, this guy goes down the page, but if we look at this as being a flat surface that we're looking down on, the potential energy is not going to change. So initially, we've got kinetic energy from object 1, kinetic energy from object 2, any work being done, kinetic energy, we'll call it initial, 1 final plus kinetic energy 2 final. So kinetic energy is 1/2 the mass times the velocity squared. He's not moving, so no kinetic energy. Plus work equals 1/2 2 times 6.7 squared plus 1/2 10, and we found his velocity. If we look back on the previous page, we found that the velocity was 0.364 meters per second. So now we can just solve this thing. If you, or when you do, please verify on your calculator that you get the same thing I get. This is going to end up being much smaller than this. We can kind of see that already. 6.7 squared is less than 8 squared. This is 64. This is going to be somewhere between 36 and 49. So already this is going to become really small. So we can see that we're going to get a small number here. And we're subtracting over a much larger number, so ultimately it should be negative. And I got that the work done was negative 8.46 joules, which is what we expect. Negative work means energy is leaving the system. Well, how is energy leaving the system? When these two objects smack together, you're going to get energy loss due to sound. They're going to clack together. And heat, which makes this thing an inelastic collision. The heat is one that you guys generally don't have a lot of experience with, because it's not like you run up to an object that just smacked into another object and put your hands on it and think about the heat loss, but there is definitely going to be heat generated there. I am not going to do example 5. If you'd like to see example 5, fire me an email. I can take a look at that for you. We're going to skip ahead to Where are you here? I'm going to actually make example 7 part of your homework. I'd like you to try it. It's similar to the one that we just did, except in this case they stick together. So this I want to make part of your homework. I'll give you the answer here. The answer to this question is V final of the pair is 1.66 meters per second, 53.06 degrees north of east. But I want you to try it. I want you to make that one part of your homework. There's one more kind of question that I want to do with you that isn't addressed in your notes formally. So I created this question. Here is example 8. A 10 kilogram plate is resting on a table and it spontaneously explodes, as plates do. So here we go. We've got a 10 kilogram plate and it's going to explode. It's going to explode into a 6 kilogram piece, a 3 kilogram piece, and a final piece, well, which we can figure out the mass of already. So we've got the 6 kilogram piece, we're told already, is traveling downwards at 4. So 6 kilograms is just more than half of this thing. So I'm going to do what I can to draw. There's our 6 kilogram piece. That's not to scale, obviously. We've got our 3 kilogram piece. This guy's moving this way. We're told downwards at 4 meters per second. This guy's moving this way. We're told that he's moving. Oh, and I forgot to put 30 degrees. So the velocity here is 4.27. And I'm just going to put this in here right away. It's 30 degrees north of west, so that guy right there is 30 degrees. And so that means we're going to have a sliver here, a 1 kilo sliver. Moving off this way, and this is what we want to try and find. We want to figure out what. So that's a 3 kilogram piece. Or 1 kilogram piece. We want to figure out what the momentum is, what the velocity is of that guy. And we have to do this, we have to use momentum. So collisions, we've looked at collisions already. One of the other, the last kind of problem that gets dealt with here is explosions. Now, explosions are similar to collisions in that ultimately the momentum has to be conserved there as well. So, the beauty with the explosions though, is that momentum initially, so I've got momentum initial equals momentum final. Initial momentum for a non-moving object is 0. We're operating in 2 dimensions though, so these have to be vectors. So what we're going to get here is we're still going to break this up into x's and y's, and we're going to take it from there. So I want my x momentum first. So 0 is going to equal a whole bunch of things. I'm going to have the mass 1 v1 x final plus m2 v2 x final plus m3 v3 x final. We've got 3 pieces here, and so we have to have 3 terms in our momentum. So this guy here, this is straight down. So this is a v final y, a v final x for this piece is going to be 0. This guy here, we can break his momentums up. So here's my vx, here's my vy. This is 30 degrees at this point. You guys should be relatively comfortable with the trig, so I'll just tell you what I got for my values here. My vx is going to be, it's moving to the left, so that's going to be negative. I got negative 3.698. Again, that's just 4.27 times the cos of 30. And it's negative because it's left. Vy is up, and I got a value for Vy of 2.135. This guy here is going to have an x and a y component, Vx and a Vy. And that's what we're ultimately looking for here. I'm going to call this piece piece 1. I'm going to call this piece piece 2. And this little guy I'm going to call piece 3. So 0 is going to equal m1, it has no x component. We're in the x section. So it's going to be 0 plus, I'm going to have my 3 kilogram piece times now my x velocity here is negative 3.698 plus my 1 kilogram piece, v3x final. So we can see this time this is going to be negative, and we're going to add it over, which is going to give us a positive velocity, which it should based on our picture here. We're going to get a v3x final of 11.094 meters per second. So I can put that up here, 11.094 meters per second. And then I'm going to slide this down here, and we're going to do the same thing with our y's. Initially, again, it's stationary. So it's going to be 0 equals m1 v1 y final plus m2 v2 y final plus m3 v3 y final. Slide this down here a little bit. Now, the 6 kilogram piece does have a y component. So we're going to get 0 equals, our mass was 6 times 4. It's downwards, so that's going to be negative. Plus, m2 is 3 times our y component there was positive 2.135. Plus a mass of 1 times v3y final. If you solve this thing, you're going to get a v3y final of, so it's going to be negative 24, which we're going to add over. This is going to be positive 6 point something, which we're going to subtract over. And so this thing is going to become 17.595 meters per second. So that becomes the y component of the velocity for this little guy up here. So that's going to be 17.595 meters per second. And now the last thing we're going to do is we're going to find the magnitude of that velocity. And this is kind of making sense. The heaviest piece is moving slowest. This guy's not moving that much quicker. This guy's flying out of here. This little chip just would suck to be whoever got hit by that. So now let's finish this thing off here. I'm going to use green. We're going to get a velocity is equal to the square root 17.595 squared plus 11.094 squared is going to give us a final velocity of 20.8 meters per second. So this thing's shooting off at something like it's between 67 and 70 kilometers per hour, which is fast. And then we're going to get a direction here. The direction I'll put down here is going to be the tan inverse. That's that angle right there of opposite 17.595 over 11.094. Gives us a direction of 57.8 degrees, and that's going to be north of east. So we can put that up here, 57.8 degrees north of east is our final there. So I'm going to leave you guys with some questions here to practice. I'll write them up top here. Remember, I want you to try that homework. Sorry, the example out of example 7. So your homework is going to be example 7. I want you to take a look at questions 4 and 5. I want you to try I want you to do 4 and 5, 8 and 10, as well as example 7 there.